So here's the next actual 3D question that I'll be covering. So we got these two tape spools. They're on this axle. So those axles are supported by bearings. I got the bearings at A, got the bearings at A, got the bearings at D. Got the two radii for the spools. This one's a bit smaller than the other. This one's got a radius. B here's got a radius of 1.5 inches. This one here's got a radius of 2 inches. And we know what the tension is in the tape B here. And this thing's rotating at a constant rate. So again, it's moving, but it's not accelerating. It's it's in static equilibrium because it's staying at constant velocity. It's staying at a constant rotational rate. It's not moving laterally at all. So the one assumption they're doing here is that the bearing at A is not going to have any axial thrust, and you can then neglect the weight of the spools and the axle, which is well, I don't know. Maybe not the best assumption, considering that the tension on the tape is only 20 pounds. So honestly, the weight of the spools and axle probably isn't completely negligible, but it's just an example. So here's a goal here. We are trying to find the reactions at A and at D. So I drew ourselves a free body diagram here. This problem is simple enough that I figured we could kind of keep it in a semi-isometric view here instead of trying to break it up into X and Y plane and then a YZ plane. That sounds like a bit too much fuss. So labeled the forces. Got the tension downwards here. I've got this unknown tension at C here. So again, this tension here, it's acting in the negative Y direction. This one's acting in the negative Z direction, because again, if X is this way, Y is this way, then we do our curl. For our right-hand rule, that gives us Z direction positive this way. So, tension for spool C is negative Z direction. Got our five reaction forces that are also unknown. So we got the AZ force, the AY force. So that was sorry, sneeze did not want to come on. So the problem stated that we're assuming that the bearing A doesn't have any axial reaction. So that would mean that the bearing D still does, and it of course is going to resist movement in the Y direction and the Z direction as well. So solving for the forces, first one's easy. Sum of the force in the X direction equal to 0. Only one that's acting in the X direction is dx, so that is 0. So again, that's why we stated that the AX is 0, so we could solve for dx as 0. If we had included an AZ in here as well, then essentially all we'd be able to solve for here is dx is equal to AX, which would be annoying. It doesn't actually tell us what's going on there. So that's why we often kind of pair those At least that's why we often for statics problems at least have one of the supports that will be resisting any lateral movement, and that might be the only force in that direction. So the next thing I'm going to do is take a moment about the x-axis. So that can be taken kind of at any point along the shaft. So basically, if we're looking at this thing, down the length of the shaft, we've got that force, and we've got that force, and everything else passes through the center of the shaft. So if we take that moment there, realize you can't quite see that. So if we take that moment there, we realize that these two forces that are acting on the spools are the only forces that are going to be causing that shaft to rotate. The supports from the bearings don't cause the shaft itself to rotate. That's the entire point of bearings. We want to hold the shaft in place and let it spin freely about that axis. Otherwise, we wouldn't use the bearings. Essentially, our sum of the moment in the x direction, about the x-axis, that's just going to be looking at this. So we've got the 2 inches from here to here, and we have the TC, and that is going to be a negative amount because, again, that is going to be causing clockwise rotation about the x-axis. The other one, got the 1.5 inches from here to here, and we've got the known amount of TB, the 20 pounds. So again, that'll be causing a counterclockwise rotation, so that'll be positive. And that just lets us solve relatively simply for TC. TC is going to be equal to 20 pounds times 1.5 divided by 2, which ends up being 15 pounds. So we got our TC. Next thing we want to be doing is basically just taking the moment about the z-axis, and I'm going to be doing that at A. So if we're looking at that, that's the moment about this axis here. So if we're taking the moment about that axis at this point, again, any forces that are acting parallel to that axis, such as TC here, or DZ here, those don't show up at all in the calculation because they're acting parallel there. So the only forces that are going to be caught, if we're just holding on to the end of, I'm going to clean this up a little bit. So if we're holding on to this point, and we're just trying to measure the tendency to spin around this axis, then the only forces that are going to cause any tendency for that to happen are our downward force TB here, and our upward force TY here. All the others are going to be causing are going to be causing rotation about different axes. So, again, we know the lateral distances. So that'll be 20 pounds times 20 pounds times this amount. It's going to give us that rotation. And on the other end, we've got 15 inches times the dy here, and that'll give us the value for dy. So in this instance, again, the the tension here from the tape, that's going to be taken about this axis. That's going to be causing a clockwise rotation. So that'll be a negative amount. The other one will be positive. So that means we can just solve for dy relatively simply. So that'll be 6 pounds. So now that we have dy, we can solve for ay just by summing the forces in the y direction. So 0 is going to be equal to ay minus the 20 pounds from the tape plus the 6 pounds from the support on the other end, means that we got our ay of 14 pounds. Next thing we do, just take another moment, not too shocking. So we're going to be going ahead and taking the moment about the y-axis. So again, this time, let's clear this up a little bit. So this time we're going to be taking the moment about this axis here. So again, forces that are parallel to that, or forces that act through that point, don't cause any rotation about that axis at that point. So this one here, that doesn't do anything. This one here does, and this one here does. dx doesn't do anything because it passes through, the line of action passes through that point, and dy here doesn't do anything because it's acting parallel to that axis. It causes rotation when measured at, it certainly causes rotation when measured at A, but it causes rotation about a different axis. It causes rotation against the z-axis. Right now we're looking at the rotation about the y-axis. So we just got those two forces that are going to be causing that rotation. So again, the tension from the tape TC here, when measured from here, that's going to be causing a counterclockwise rotation, and the other force here is going to be causing a clockwise rotation. So this will be negative, this will be positive. So there we go. We got the 15 pounds for the tape at TC times the distance. I got the 4.5 plus 6 from here to here. And then we got the 15 inches, the negative moment here from dz, so that'll be minus 15 inches times dz. Let's just solve for dz. That'll be 10.5 pounds. And once we have that, just to add up the total forces in the z direction. Got a reaction at A minus the 15 pounds for the tension in the tape. Again, keeping in mind that our z positive direction is this way. So reaction at A, the negative force at T, and we also have the positive reaction at DZ, 10.5 pounds. So our AZ ends up being 4.5 pounds, and that's all we've been asked to solve for.